Hey everyone, welcome back to the channel. In today's system design breakdown, we are building something simple yet powerful, a URL shortener just like tinyurl or bit.ly. This is one of the most frequently asked system design problems in interviews. So stay with me as we break it down step by step in a beginner friendly way. So the goal is simple. We want to take a long URL, say a giant Google Docs link, and convert it into a short, shareable version like /abc123. And when a user clicks that short link, they should be redirected to the original one. So before proceeding ahead, let's analyze functional and non-functional requirement, right? So the functional requirement should be like the functional requirement includes like our system should accept a long URL and return a short one and redirect users from the short URL to the original one. So this is functional requirements. Now let's understand non-functional requirement. So for non-functional, our system should be highly scalable, very high availability, and should have very low latency, so that in no time it should be redirected to the original URL, and it should not take time to store the same URL, right? So, how does it work? Let's understand it. At the heart of the system, we generate a unique short code like ABC123 for every long URL. We then store this mapping in a database. So, when someone hits short.ly/ABC123, we can look it up and redirect them, right? So, before proceeding ahead, you should ask your interviewer a few questions to clarify. Uh, like, for example, what should be the length of the short URL? Like, how many digits according to the requirement? What should be the length of the short URL that we are going to generate? And what is the traffic you are looking at? Right? So there can be like billions of millions of hit per second. So according to that, you have to design our system, right? And the third question should be like how many unique URL will come for shortening and for how long we need to store it, right? So whenever we design this system, so we should also keep in mind like for how long we are going to keep that short URL in our database, right? So that there should be like cleanup service also. We should keep it clean after a few years, like for 5 year or for 10 year, right? And the last question should be like not last but yeah, the other question should be like which character should be included in short URL, right? So are we going to include small case, capital case, letters and numbers, or apart from this are we also going to include a hyphen, slash, like that kind of character, right? So these questions should be asked with the interviewer before proceeding ahead, so that interviewer will know that yeah, you are clear in your concept, and like there should be two-way communication, right? You should not just start designing the diagram and like that, right? You should not cram it. So most now let's understand how to generate short codes, right? So there are different way to generate the short code. For example, there are three common approaches. The first one is like base 62 encoding of a unique ID. So basically what we do, actually we basically do base 62 encoding, and also we take a counter like increment ID, and we try to encode that counter from base 10 to base 62. And the other one is hashing the URL, but there is a chance of collision, so, right? So we have to handle the collision in a hashing. And the third one is like by the help of UUID, we can generate a random number, but it might get longer. So that's why most real world system use base 62 encoding with auto increment ID, which is simple, fast, and avoid collision. So in this scenario, we are going to use base 62 encoding with auto increment ID, right? And basically here we are going to take six character. The first question which is being asked, what should be the length of the short URL? So I am assuming like we will be getting for like less than 60 billion of unique URL. So if we do 62 ki power 6, it will be approx 56.8 billion, right? That's why we are going to take 6 character. So now let's, before proceeding ahead and jumping to diagram, first of all, let's analyze the capacity estimation and constants, right? So let's estimate the traffic. So assuming we will have 500 million new URL shortenings per month, with 100 is to 1 read write ratio, we can accept 50 billion redirections during the same period. For example, if we multiply 500 million into 300, because we are assuming 100 is to 1 read write ratio, right? So it will become 50 billion. Okay. Now let's calculate the queries per second. So we are getting 500 millions new URL per month. So if we divide it by 30 days into 24 hours into 3600 seconds, so it will become 200 URLs per second, right? So considering 100 is to 1 read write ratio, URL redirection per second will be, so we are considering 100 read ratio, 100 is to 1 read write ratio, right? So we'll multiply this 100 with 200 URL, so it will be approximately 20k per second. So there will be around 20,000 hit per second per read. Okay, so this was the traffic estimate. So per second, our database is getting hit by 20,000 URL. So this was the traffic. Now let's estimate the storage, right? So before designing any system, we should know like how much storage is needed for what period of time. So let's assume we store every URL shortening request and for 5 years. So we are assuming here we will be storing URL for 5 years. Since we expect to have 500 million new URLs every month, the total number of objects we expect to store will be 30 billion. So if you multiply 500 million for 5 years into 12 months, it will become 30 billion. So we are going to get 30 billion new URL within 5 years. And for storage, we have to assume how much storage is needed per URL. So let's assume that each stored object will be approximately 500 bytes. We will need around 15 terabyte of total storage. So if we multiply this 30 billion with 500 bytes, so it will be around in 1 billion, it is almost 10 to the power 9 zero, and this 3 zero, so it will become 10 to the power 12, which is 1 TB, and if you multiply 5 with 3, it will be around 15 terabyte. So we are going to need storage of 15 terabyte. So this was the storage estimation. Now let's go to bandwidth estimation. So for write request, since we expect 200 new URLs every second, total incoming data for our service will be around 100 kilobyte per second. So 200 into 500 bytes, it will become 100 KB per second. So for read request, since every second we expect 20,000 URLs redirection, total outgoing data for our service would be around 10 MB per second. If we multiply 20,000 with 500 bytes, so it will become around 10 MB per second, right? So our bandwidth should be greater than equal to 10 MB per second. Now let's estimate the memory. So if we follow 80-20 rule, meaning 20% of URL generates 80% of traffic, we would like to cache this 20% hot URL. Since we have 20,000 requests per second, we will be getting 1.7 billion requests per day. So like 20,000 requests into, if we do 24 hours into 3600 seconds, so it will become around 1.7 billion, and we have to cache 20% of these requests. So we will need around 20% is 0.2 into 1.7 billion, and each URL will be taking 500 bytes, so it will be around 170 GB. So we'll be needing memory of 170 GB, okay, to for like to cache 20% of hot URL which is I mean, which is frequently being used, right? So we need to cache that URL so that our database will not get hit multiple times. Okay, so now here is the system. This is the simple system without any multiple services or without any cache. Okay, so basically here what we are doing here, user is submitting long URL and server generates unique short code, store mapping in database, short URL is returned, and on visit server looks up short code and redirects, right? So now let's optimize this system. So basically we have sort URL service and we have a database. We are choosing NoSQL database because we are going to dump our data. We don't need any relation between two tables. We just need like in schema, we need ID, short URL and long URL. So there is no any mapping between table. So that's why we are using NoSQL database, and we are using load balancer because later on we'll be using multiple services, right? So to distribute the load, equal load between the services, we are using load balancer. Okay, so now what is the drawback in this system, right? So first of all, look, there is a sort URL service, so there is a single point of failure, right? If this service goes down, so our whole system will goes down. Similarly, the database, we are using only one database, similar for database, right? We are not using any cache. So, and since we in non-functional requirement, we written like our system should have low latency, and here we are not using any cache, so the latency increases, right? So let's optimize this system. Okay, so here what we have done basically, if there are multiple instances of service and all of them are getting some request, it is possible that multiple service can generate same short URL, and we will end up with collision, right? So what we want basically, we want to generate a unique ID, and we don't want to have duplicate ID for two different URL, right? So but in this scenario, like we have used multiple instances of service, but in this scenario what happens, like let's say we are getting any from user 1, we are getting any URL from user 2, which is requesting a second URL to generate the short URL. There might be chances like they can generate same ID, and for that the same short URL generated, right? So there is a chance of collision. So you might be thinking like maybe we can check the database and retry, but it is not efficient solution, right? It will increase the latency. So let's optimize again this solution. So this is the solution where collision don't occur. So here what we have done, basically we have used the Redis cluster, right? So we have added Redis cluster, and all of these services will request number from Redis. Redis makes sure that it will always return unique number. So this Redis cluster makes sure that it will return a unique number, which will be which will be taken by this short URL service to generate the short URL, right? So the problem here is every service is connected with Redis, right? So it is under huge amount of load, and there is a chance of single point of failure. And if cluster goes down, then there is no any backup, so our system crash. So what is the alternative? So to keep multiple Redis that will give high availability, it will work fine till the time Redis don't give duplicate number. We need to manage what series are given to whom if we give series to each Redis. So basically, if we keep multiple Redis also for high availability, it will work just fine. But until Redis don't give duplicate number, right? Let's say we also included this Redis cluster. So there is also chances in the future, right? They can generate a duplicate number because there is no any communication between them, and we need something to manage this cluster, right? so that which will assign the series of number to each cluster. So this is also not the optimal solution. So let's move again towards efficient solution. Okay. Okay, so here what we have done is, here we have created errata token service, right? Which runs on top of MySQL, and basically token. What does token service do? Whatever the instances short URL service we have, basically they assign a range of number to each services, right? Each token service gets request which run on single thread model. It gives range to any of the service instances. So basically, let's say if we have multiple like two services, so what it does, it assign a range, let's say for 1 to 5k to this first service, again 5k to 10k to this second service, right? And let's say if these services uh, finish this number, this counter number to generate the sort URL. So it will again request with the token service. Give me again the other range of series. So again, this token service, what it will do, when it assign the range of series, basically uh, it marked in its memory that it has been assigned, and it will never assign that series again, right? So here it will again request to the token service, and it will again provide to short URL service a series of number. Okay, so what is the problem here? The If anyhow, let's say short URL service goes down or killed, then range assigned to that will be lost or never used, right? So basically here we are using, we are basically, what happens when any short URL service system goes down, so our range of service will be lost, range of series will be lost, and since we are not keeping track of that, and since we have I mean billions of ranges, we don't have to worry about that. And if we track those token, then it will be, our system will become complicated. If we track those token, that then it will become complicated system. So why Cassandra? So we are using Cassandra here as a database because trillions of record in MySQL is not efficient and scalable, right? So this is the system, and here basically, yeah. So now here we can do other enhancement also, like to improve speed, especially for redirection. We use caching with Redis or Memcached. Popular links can be served directly from the cache, skipping the database. So before reaching database, maybe we can use cache here, and before finding from database, we can first find from cache. If it is there, we can return directly from there, right? And for to make it more scalable, we will need load balancer in front of app servers, read replicas, or a distributed database. We can possibly use a CDN to cache redirects globally, right? And we can also use extra optimal features like, if we want to make it production grade, we can add analytics for each short URL, let users create accounts and view their links, set expiry dates for temporary links, right? And so that's the full breakdown of how to design a URL shortener. It may seem simple, but there is a lot happening under the hood, from code generation to performance and scaling. If you found this video helpful, don't forget to like, subscribe, and hit the bell icon for more system design breakdowns. Drop a comment if you want a similar video on designing WhatsApp, YouTube, or a scalable chat app. Right? Thank you.